Okay, parametric functions notes. You've done polar functions, now you get to do parametric functions. Woohoo! A parametric function, as written here, is described by a pair of equations, one for the x-coordinate and one for the y-coordinate, both of which are functions of a third variable called the parameter. Since x and y are both often functions of time, the variable t is usually used for the parameter. These graphs are particularly useful for talking about how position changes as a function of time. So we'll look at some examples of that tomorrow. These are all represent a parametric function. So this is a parametric function, a pair of equations. The only difference in the second two is just the notation. Instead of just saying x and y, this is x sub t, y sub t, or x of t, y of t. So we're both saying that x and y are both functions of t. Now to graph a parametric function by hand, we make a t-chart, but now it has t, x, and y in it, not just x and y. We pick values for t, we plug values for t into both equations to find the values for x and y at a particular value of t. So if I plug -3 into the first equation, I get -6 plus 3, which is -3. If I plug -3 into the second equation, I get -3 minus 1 squared, which is 16. Now if I plug -2 in, I get -4 plus 1, which is -1. Plugging -2 here, I'd get -3 squared, which is positive 9. And if I continue on in that manner, I'm going to get 1, 4, 3, 1, 5, 0, 7, 4, and 9, 9. So notice that in my first equation, in the x's, it's just a linear equation with a slope of 2, so it's going up 2 every time. With the y, if it's a quadratic, these are a number squared, so look at all of our y values are perfect squares. Now the next thing I do is to plot these points. I don't plot the t. The t is kind of a hidden underlying variable behind the x and y, sort of a behind the scenes variable, but I'm going to plot the x and y points. Unfortunately, -3, 16 doesn't fit on the graph, so I'm going to start with -1, 9, which goes here. Then 1, 4, then 3, 1, then 5, 0, then 7, oops, I did these wrong. This is supposed to be a 1 and a 4, sorry about that. 7, 1, and let me plot that in the right place. 7, 1, and 9, 4. And you can see this is a parabola, or at least it appears to be, and it is a parabola. Now, before I draw little arrows on the end like I'm used to doing, 3 says add arrows to show the direction of the curve as t goes from smaller to larger numbers. And in this case, as t gets larger, the graph moves from left to right. Now that is not always the case, so don't always assume it's going to move from left to right, but that's where we add the arrows. So arrows indicate t getting larger. Okay. Now, graphing on the calculator. I did make a little mistake in this graphic down here. I meant to graph the t plus y, x equals t, 2t plus 3, and y equals t minus 1 squared, but I accidentally wrote t plus 1 squared here, so this should say t minus 1 squared. On your calculator, you're going to, let me open up my calculator. I'm going to start a new graphing page. So let me just do a new graphing page. And just like we did for polar, we're going to go to Menu, Graph, Entry, and Edit, and then to Parametric. Notice then we have an x of t and a y of t. Since I did this in the previous class, and mine's x2, yours is probably saying x1. And I'm going to type in 2t plus 3 and t minus 1, the quantity squared. And if I push graph, or push enter now, I get a graph. But notice it's not the whole graph. It's not the graph that you saw before. It's only part of the graph. It starts right here. And if we were to trace this, and I should have traced in the other class, but if we were to trace, let me go to Menu and Trace, Graph Trace. notice that if I type in, I'm going to type in 0 for t, that starts the first point. And if I trace, it's tracing values for t. But what if I went backwards? Okay, it's not going to let me do that at all. It's going to jump to something else completely different. I think I'm going to push Control, Escape, Control. Oh, let me go to Zoom. I'm going to go to Zoom. This is not what I wanted this to happen. Let me go to my window settings, Zoom standard. Okay. Tab. Wow, it just kind of, that's weird. Well, this is really messing up. I'm going to put in my 2t plus 3 again. And my t minus 1. So much for showing something on the fly. That didn't work terribly well. But anyway, there's my graph again. Why is it only showing part of the graph? That's the big question. Now, for those of you who may not have realized, this is a little helpful tip. If you push Tab and then you up arrow, it'll get you back to what you typed in before. And I want you to notice this little line right here, 0 less than or equal to t less than or equal to 6.28. Notice that I only have positive values for t, no negative values. Whereas when I graphed it by hand, I used some negative values for t. So I'm going to include some negative values. I'm going to back that off, and I'll go ahead and put -6 since I have 6.28. Doesn't really matter here. That'll be enough to show. Notice there I get the negative values. Because when t was equal to 0, I got this point right here, which was y was 1. So I only got that part of the graph just when t was positive. So if I want all of the graph to show, I need to include all the values for t. So to make sure that you see the entire graph, include a larger range of values for t. Particularly negative numbers. Now there are cases where negative numbers don't make sense in the context of the problem. But if you need to see more of the graph, that would be a good place to start, would be to include some negative numbers. Now how do we go from parametric form back to rectangular form? We learned to do that with polar. We're going to do that now with parametric as well. The way you do that is you have a pair of equations. You're going to solve each of the pair for t. So I'm going to just start by writing x equals 2t plus 3 and y equals t minus 1, the quantity squared. So solving the left-hand one, I would subtract 3 and then divide by 2. And that would give me my t. On the right-hand one, I would take the square root of both sides. So if I take the square root of both sides, remember I have to use plus or minus. This would be plus or minus the square root of y equals t minus 1. If I solve this for t, this would be 1 plus or minus the square root of y is equal to t. Now, because both of those are equal to t, I can set the two expressions equal to one another. And I can say, draw a line here, x minus 3 over 2 is equal to 1 plus or minus the square root of y. And I want to pretty this up a little bit. This doesn't look very nice. Particularly, I don't like having the 1 plus or minus the radical in there. It doesn't look very nice as an equation. You might guess that I'm going to want to square both sides, but before I square both sides, I would like to clean this up a little more and get the radical by itself. The easiest thing to do is get rid of the fraction first, because if I subtract 1 from both sides, then I have kind of a messy looking thing on the left-hand side. So I'm going to multiply both sides of this equation by 2. And when I do that, I get x minus 3 is equal to 2 plus or minus 2 the square root of y. Then I'm going to subtract 2 from both sides. I get x minus 5 is equal to plus or minus 2 the square root of y. And now I'm going to square both sides. And the nice thing about this is that gets rid of the plus or minus now, because it doesn't matter once I've squared it that there's a plus or minus there. So I have x minus 5 squared is equal to 4y. This happens to be in the form of a parabola in standard form. X minus h squared equals 4p times y minus k. Remember that? In this case, my vertex is the 0.50, and p is equal to, 4p is equal to 4, so p is equal to 1. Now, you're not always going to be able to do this. This happened to turn out really nicely, so I thought I would just show you that if we go back and look at our graph, you'll see that this actually works. Here's our p, 1 away from the vertex. So there's our focus. And if we go to the left 2 and to the right 2, you'll see that the lattice rectum is indeed 4, so p equals 1 and the lattice rectum equals 4, and that makes sense, makes perfect sense. It's an x squared, so it's opening in the y direction and so forth. So this would be one way, one nice way to leave your equation. Another, or you could say y is equal to 1/4 times x minus 5 squared, because that's also a nice way to leave the equation. So that would be fine as well. But basically clean it up, make it look like something typical for a parabola. This is all the notes for today. On your homework, you're going to be doing some of the problems are very similar to what we just did on the notes. Then on this, that's pretty much on the first side. On the second side, then you're going to be graphing some equations in parametric form that have sine and cosine and tangent and secant in them, and you're going to see what that graph looks like, and then based on what you see, write the equation. Don't use this method to write the equation, but just base the equation on what you already know about the figure, and you'll see what I mean when you do that. And once you see I want you to start seeing the connection between the rectangular form and the polar form for those particular figures, and see if you can come up with some general thoughts about that. So that's the second part, and then we'll kind of build on that tomorrow and continue with the notes. That's it. Have a nice day.